electric flux density defined with symbol D. So this electric flux density is defined as D is equal to epsilon naught E. Epsilon naught E. So this is the physical meaning of this electric flux density is in a given area how many field lines? How many field lines are exist? So field lines in a given area, nothing but a flux density. So density here means the sense that in a given area. So electric flux density is epsilon naught E. So electric flux phi is given by integration of S, integral over S d dot ds. Integral over S d dot ds. That is, if you integrate over the entire surface, the electric flux density, you will get a flux. So this is the relation between electric flux and flux density. So you can calculate electric flux density due to charges, because the only thing is here we are multiplying with epsilon naught. So whatever the formulas we discussed so far also applicable to calculate electric flux density also. The only thing is first calculate electric field and multiply with epsilon naught. Now we will discuss very important concept, Gauss law. It's called Gauss law. So this is one of the fundamental law of electromagnetism. So this Gauss law is useful to derive the first Maxwell's equation. So entire electromagnetics is nothing but 4 Maxwell's equations. Maxwell defined the entire electromagnetism with the help of 4 equations known as Maxwell's equations. Electromagnetics is nothing but Maxwell's equations as well. So the first Maxwell equation is derived from Gauss law with the help of Gauss law. So Maxwell's equations starts here. So first of all we will discuss what is Gauss law. Then by using Gauss law how Maxwell derived the first Maxwell's equation we will see. So Gauss law states, what is the statement of this Gauss law is, Gauss law states that the total electric flux psi through any closed surface is equal to the total charge enclosed by that surface. The total charge enclosed by that surface. This is a Gauss law statement. That is, the total electric flux through any closed surface. So closed surface, suppose this is a closed surface. Closed surface is nothing but we know closed surface is nothing but a volume. Closed surface is nothing but a volume. So the total electric flux coming out from this closed surface or volume is nothing but Q enclosed, the total charge present in the volume. So field lines generates because of charge only. So Gauss states that the total electric flux through any closed surface is equal to total charge enclosed by that surface. That is, total flux psi is equal to Q enclosed. But I know this is the volume, total charge enclosed in the volume. Suppose this is volume charge density rho v. Suppose the volume has a volume charge density rho v. Then total Q enclosed is given by integration over V rho v dV. So this is equal to psi, that is equal to psi. But psi is equal to total flux is integration over closed loop surfaces d dot ds, where d is electric flux density, so that I can relate these two. Therefore integral over s d dot ds is equal to integral over v rho v dv, integral over rho v dv I can relate. But already we discussed divergence theorem. That is, apply divergence theorem here. Apply divergence theorem. So according to divergence theorem, what? Divergence theorem relate closed surface integrals to volume integrals. So according to divergence theorem, integral over s d dot ds is equal to integration over v del dot d dv. Therefore I can write integration over this left hand side as integration over v del dot d dv is equal to integration over v rho v dv. If you compare these two equations, that implies del dot d is equal to rho v, where rho v is the volume charge density. Del dot d is equal to rho v. This is the first Maxwell's equation. So this is known as first Maxwell's equation. Del dot d is equal to rho v. This is also known as Maxwell's equation in point form. This del dot rho v is known as Maxwell's equation in point form or differential form. Whereas this this is known as Maxwell's equation in point form or a differential form. This is this one. Suppose this one. Now we can write after this we can write integration over s d dot ds is equal to integration over v. Rho v is nothing but del dot d. Of course, this is based on divergence theorem only. dv. This is integral form. This is integral form of Maxwell's equation. This is point form of Maxwell's equation. So this is known as first Maxwell's equation. Del dot d is equal to rho v. So what is the meaning of this del dot d is equal to rho v is del dot d. So nothing but the diverging flux density is nothing but volume charge density. Here we are talking about charge densities. So the flux density diverging is nothing but the volume charge density. So that is the first Maxwell's equation in a point form. This is the integral form. Suppose this is a volume. V. Here it is a 10 nanocoulomb charge. It is a minus 5 nanocoulomb charge, like this. Then what is the flux leaving? Flux leaving is equal to how much? So by using Gauss law, the total flux leaving is nothing but charge enclosed. Total charge enclosed in the volume. So here total charge enclosed in the volume is 10 nanocoulomb minus 5 nanocoulomb. That is equal to 5 nanocoulombs. The total flux leaving is 5 nanocoulomb. So like this we can explain Gauss law. Now we will work out some problems based on Gauss law. The first problem is, problem 1 is, let d is equal to z into rho cos square phi az cap coulomb per meter square. So this is the flux density given. Then what is the charge density? What is the charge density? What is the charge density at 1 comma pi by 4 comma 3? 1 comma pi by 4 comma 3, and the total charge enclosed by the cylinder, the total charge enclosed by the cylinder of radius 1 meter, with minus 2 less than or equal to z less than or equal to 2 meters. So this is the problem. So how to solve this problem? The solution to this problem is, here we have to solve for two questions. The first one is, here d is given, z rho cos square phi. So here it is given in terms of cylindrical coordinates. Then what is the charge density at 1 comma 5 by 4 comma 3? So charge density is nothing but here volume charge density. So here why volume charge density is, here cylinder given, cylinder radius given. So what is the total charge within the volume? So charge density is rho v is equal to del dot d by using Maxwell's equation. So that is equal to divergence formula. Here we have to apply divergence formula for cylindrical coordinate system. Remember, you need divergence formula for cylindrical coordinate systems here. Of course, here if you observe this d value, d is given, only az component is given. So cylindrical components, this is d by dou z az. That is equal to, suppose if it is given a rho also a phi, then you have to apply the formula of cylindrical coordinates. So directly here I am simplifying here, dou by dou z of az, that is equal to rho into cos square phi. So here they are asking at a particular value, 1 comma pi by 4 comma 3. So rho is equal to 1 cos pi by 4. Cos pi by 4 means 1 by root 2. So 1 by root 2 whole square, 1 by 2. So 1 into 1 by 2, that is 0.5 coulombs per meter cube. 0.5 coulombs per meter cube. So this is the charge density. And next one is, what is the total charge enclosed by the cylinder? So total charge enclosed by is nothing but integration over v rho v dv. So this is equal to integration over v means along rho phi z. So rho is given 0 to 1. Phi is 0 to 2 pi. Z is equal to minus 2. Minus 2 to rho v dv. So rho v is equal to rho cos square phi. We calculated here. Rho cos square phi. So rho cos square phi dv. dv means, what is the differential volume of a cylindrical coordinate system? Cylindrical coordinate system is rho d phi dz. So here the differential volume element is useful here. So if you simplify this, this is nothing but rho square d rho. So integration over rho square d rho means rho 2 rho cube by 3. Integration 0 to 1 pi 0 to 2 pi, and z minus 2 to 2. So if you simplify this, you will get 4 pi by 3. 4 pi by 3 as answer. 4 pi by 3 coulombs. Here integration rho square means integration rho square is rho cube by 3. Here it is not phi, this is cos square phi integration. So you have to, this is cos square phi, you have to simplify and simplify this entire integration. You will get 4 pi by 3 coulombs as the answer. So calculate the integration and verify the answer. Next problem is charge in the form of plane sheet with the density rho s equal to 40 microcoulomb per meter square is located at z is equal to minus of 0.5 meters. A uniform line charge of rho L equal to minus 6 microcoulomb per meter lies along the y-axis. What is the net flux? What is the net flux crosses the surface of a cube of side 2 meters centered at origin. So this is a given problem. So the solution to this problem is, so here first of all what is given, draw a rough figure so that you can analyze the problem very easily. So x, y, z. So here first of all here given lies along the y-axis. What is the net flux crossing the surface of a cube of side 2 meters? Cube of side 2 meters. Centered at the origin. So here I am drawing a cube of side 2 meters each. Centered at origin. So this is the cube of side 2 meters. Centered at origin means above is 1 meter, below is 1 meter. Above is 1 meter and below is 1 meter. So here it is given a plane sheet with density rho s is equal to 40 microcoulomb per meter square is located at z is equal to minus 5. So this is z is equal to 1, this is z is equal to minus 1. Because the cube size is 1. Cube side size is 2 meters. So above 1 meter, below is 1 meter because the cube is centered at origin. So here now given at z is equal to minus 0.5 meters, a uniform plane sheet is located. So z is equal to minus 0.5 means this. So here a sheet is located like this. This is the sheet. So the sheet is within the cube itself. Now a uniform line charge of rho L minus 6 microcoulomb per meter lies along the y-axis. So along the y-axis, so this is minus y-axis. Along the y-axis, rho L is located. So this is rho s. Then what is the flux crosses the surface of a cube of say 2 meters? Then what is the flux crossing the entire cube? Then they are asking what is the flux crossing the entire cube. So by using Gauss law, we know that by using Gauss law, The total flux leaving is nothing but total charge enclosed in the volume. So here the total charge enclosed in the cube we have to calculate. So here sheet. So sheet is rho s. So we know that Q is equal to rho s into area. Rho s into area. So this is 40 microcoulomb, 40 microcoulomb per meter square into area. What is the area of the cube? So here if you calculate area cube size is 2 meters. So 2 into 2, 4 meter square. So meter square cancels. This is 160 microcoulomb due to sheet. Q due to sheet. Similarly, Q due to line charge is given by rho L into L. So rho L is given minus 6 microcoulomb per meter into L. What is the length? So only 2 meters. Length is 2 meters. Only 2 meter of length. The cube is only for 2 meter length. So it is minus 12 microcoulomb. Therefore total charge enclosed is 160 minus 12. That is 148 microcoulombs. The total charge enclosed is 148 microcoulombs. So this kind of problems are very interesting. So you can directly calculate what is the total flux living through the cube, which is 148 microcoulombs. So we can expect this type of questions in the examination.